Alright, welcome to page 2 of iterated integrals. And now what we're going to do is we're going to evaluate this iterated integral. And if you notice, it's the same integral that we have. It's the same function, but instead of, having, our y's come first, or our y's in the middle, in this case, our x's are in the middle. And you don't need to worry about that, this little f right here. The f really shouldn't be there. Alright, I'll probably take it out before you do it on the notes. What we're going to do is we're going to, evaluate the same a very similar double integral, but now with the same function, but now we're going to do it with respect to x first and then y. And let's see what we get. Maybe something might pop up. Yeah, who knows? So we're going to go ahead and take the integral of the inside. So we had the integral from 1 to 2. We're going to go ahead and integrate. So 4x cubed is just going to be x to the 4th. Minus, and then 9x squared is going to be x to the cube over 3. So 9 over 3 is 3. So 3x cubed y squared. And then we're going to go from 1 to 0 dy. Now I'm going to go ahead and plug in 1 and 0. And so I'm going from 1 to 2. And when I plug in 1, I get 1 minus 3y squared. Minus, plug in 0. 0 is going to cancel everything out, so we're just going to get 0 there. Dy. And so we're left with just the integral from 1 to 2. That's an ugly looking integral. So 1 minus 3y squared. I'll just go ahead and write that first. I don't want to integrate it yet. So 1 minus 3y squared, and then dy. Alright, so let's integrate that. So when we integrate 1, it's just y. When we integrate 3y squared, it's just y cubed. And the integral from 1 to 2. And let's go ahead and substitute in. We get 2 minus 1. 2 minus 2 to the 3rd, so 8. Minus, and then we have 1 minus 1. So that's going to give us 0. 2 minus 8 is going to be negative 6. And so again, we find that the double integral, or the iterated integral, is going to be negative 6. So hopefully you do notice that, for example, 1, same function, but our pathway went through y first. Example 2, same function, but our pathway went to x first. And we got the same thing. So you notice these things, and this is very similar to Clause's theorem on the equality of mixed partial derivatives. And so just as you have, the partial derivative of, of a function x, doing the partial of x and then y, we know that's, I'll write it instead of talking. So if you recall Clause's theorem, it's just, if we take the partial derivative with respect to x first and then y, that's just equal to the partial derivative of the same function with respect to y first and then x. They're equal. Well, it's the same. It's the same principle here, where we can, do the integrals. We can choose, once the integral or the, our space is defined, we can choose, well, what do we want to take the integral of first? Do we want to take the integral of x first, or do we want to take the integral of y first? And it just depends on, when we look at it, what seems to be the easier path, and that's going to be totally up to you. You can choose the path, you're still going to get the same answer. All right, so that leads us to Fubini's theorem. All right, is, I can choose the pathway that I want. Given the same function, I can choose to, I forget, this is where my iPad is kind of messed up. So I have to scroll up. We can, go through the pathway of y first, or we can go through the pathway of x first. We can decide which pathway we want to choose to go through first. Alright, once we do that, that's up to you. Then it's just like we did. We take the partial derivative of the inside first, and then do the partial derivative of the outside. Alright. Now, here's a special case. So let's look at 5 real quick. So if we have a function, right, that is, don't want it to capital F, let me just write a lowercase f. So if we have a function in both variables, it's just the product of, a function defined by x times a function defined by y. And so we'll say g of x times h of y. If we have a function that is just the product of two functions, one in x and one defined by y, what we can do is we can take the integral of the x times the integral with respect to y, right? Where, our rectangular area is defined by, from A to B for our x components and C to D for our y components. So now, why is that the case? Well, the case is, say, let's go ahead and take, an integral from A to B of our function and then C to D of our function f of x, y. And then, so CD will correspond to dy, and AB corresponds to dx. Well, our function f of xy is really going to be, so I'm going to write my integral the same. A to B, C to D, our function f of xy is g of x, h of y. dy dx. Now, if we're taking the integral with respect to y first of what's on the inside, what we are going to do is we're treating g of x like it's a constant. And what do we know we can do if we have a constant in the integral? Well, we can just take it to the outside. So we take this integral to the outside. We're going to get this, the integral of a to b, and then we'll pull out our g of x on the outside, and then we have the integral of c to d, h of y, dy, dx. Alright, and so then, therefore, what we can do is we can just go ahead and put our d of x with our g of x, and so that's why we're able to take the integral from a to b and g of x dx times the integral from c to d h of y dy. And so that's why, theorem 5 holds true. All right. So, again, if we have the product of, two functions in x and y, the smart thing to do is to break up the integral, and one with respect to x and the other with respect to y. So we're always looking for that, and the reason why is because it's going to make our work a lot easier. So let's look at the next one. Calculate the iterated integral 1 to 3, 1 to 5, natural log of y over xy dy dx. Well, notice here, it's no addition, subtraction sign, so I realized, oh, hey, here's a product. And so what I can do is I can break up the integral from 1 to 3, and 1 in just terms of x, which is going to be 1 over x dx times the integral of, from 1 to 5, natural log of y over y is of dy. Now, again, hopefully you see, 1 over x times natural log of y over y is going to give us natural log of y xy. So we just broke that up into the product of two functions, one in x, one in y. And so now it's a lot easier to integrate. To integrate the first, it's just going to be the integral of integrating 1 over x is just going to be natural log of the absolute value of x. And let me move up because this is where my iPad doesn't work. From 1 to 3. And now for the next one, what we could say is natural log of y over y, we could just use substitution, because we can make u natural log of y that means that du has to be 1 over y dy. And so really, what we're looking at is the integral from 1 to 5 of just u. I don't want to say 1 to 5. We have to change it. But I'm going to go back. So here, let me just not write 1 to 5. So we're doing the integral of u du. And so that's all I have to do to integrate. You know what? Let's go ahead and change. Do I want to change? No, let's just not. So if I do the integral from... Let's change it. Okay. So if we substitute in 1 into natural log of y, natural log of 1 is going to give us a 0. And then do the same, plug in 5 to get our upper bound. So natural log of 5 is just going to be natural log of 5. That's why I didn't want to do it, because I didn't want to have to write natural log of 5 up here, but yeah, that's okay. So now if I integrate this, I'm going to get u squared over 2, or 1/2 u squared from natural log of 5 to 0. Again, the reason why I changed my bounds was because I went to u substitution. Alright, so then now I have this times the integral of 1/2 u squared 0 natural log of 5. Alright, so let's go ahead and plug in. I'm going to have natural log of 3 minus natural log of 1. That's nice, that's 0. Times 1/2 natural log of 5 squared minus 1/2, and I could have pulled the 1/2 out. 0 squared, and that's equal to natural log of 3. I'll just say 1/2 natural log of 3 times natural log of 5, and then that whole thing squared. Alright, and that's it.